Yeah, so thanks a lot to the organizers for the invitation and for giving me the chance to speak here and to come to IPAM again. Actually, the last and only time I've been here was in early 2009. Right. So thanks also to the Julian Schwinger Foundation. In fact, that's the second Julian Schwinger workshop in half a year where I've been to. And there's another common thing. Also there, I decided to change what I talk about. So not on such a short notice. So actually, I decided to change the topic this morning during the morning session, which is something which has never happened to me, that I decided so late to change the topic of my talk. So there are several explanations for that. The boring one is that I felt it would actually fit better with the audience here, to the extent I could judge the audience after watching the audience interact with the speakers in free talks. And that I also like giving Blackboard talks. I don't know, maybe it's just that I'm tired from the jet lag or going to a midlife crisis, and that's why I decided I had to change things. Or it has to do something with IPAM, because at this 2009 workshop, Frank Fastrate gave a talk about where reduced local density matrices played an important role, which also play an important role in my talk. And a point he made is that all the physics is in the reduced local density matrices, and Matthew Fisher got very upset and they got in a big fight about that. So my talk will also be about local reduced density matrices. Okay, so with that, let me start. Okay, so what will this talk be about? So this talk will be about finding ground states, in particular specifically finding ground state energies, but this can be generalized to other settings. Right, so motivation. So we're looking at the ground state problems. So we are given some local Hamiltonian. I mean, many of the things I'm saying can be generalized. So we have a quantum spin system, say. Again, there's many generalizations one can think of, some of them quite straightforwardly, some less straightforwardly. And for simplicity, let's just consider a one-dimensional spin chain. So we have a one-dimensional chain of some D-level systems. So each of them is described by some Hilbert space CD. And we have a Hamiltonian consisting of terms which have spatially local interactions. And again, for simplicity, let's say these are two-body terms and they're all translation invariant. All of that is not particularly important, but it will make our life easier in writing things down. So this would be translation invariant and two-body nearest neighbor for the purpose of the talk. And what we want to do is we want to determine the ground state energy, or ground state energy density, maybe, let's say, which is given by the minimum over all quantum states divided by 1 over n or something like that. If I have some n-body system, say, on a ring. And well, another way to write that is to say that what we do, right, so we minimize over all states. But of course, the energy will really only depend, well, these are two-body Hamiltonian terms, right? So we can write this as, if we use translation invariance, there is really only one term, H2. We can write this as, well, each term contributes the same energy, so the n drops out. So we have to minimize over all psi with respect to psi, H2 psi. But now, of course, what this means is that this energy here only depends anymore. So if we just continue here, this only depends on the two-body reduced density matrix of the state psi. So what we really have to do is we have to minimize the trace over the two-body density matrix, rho 2 of this H2. And we have to minimize over all rho 2, which are compatible with some suitable global state. So I could say they should be compatible with a global state psi, but I'm using translation invariance. So in that case, I should insist that the state is translation invariant, and you might object that there are subtleties, and you might be right, and they can be solved. But if we want to make our life easier, we can just say these should be compatible with some global density matrix, right, which could be pure or mixed. The minimum can be taken for a pure state. And this one should be translation invariant. Then we are certainly fine. So what have we achieved? Well, we have taken this problem where we have to optimize over this exponentially big state vector, right? what we're looking at is a scaling in the number of sites, n. So this state is exponentially big in the number of sites, to a problem which has a constant size. But of course, we have to pay a price. We have to define an optimization set, right? So this ρ2 is an element of some set S. And this would be the set of all allowed reduced density matrices on two sides compatible with some translation variant state. So this arrow is supposed to be incompatible with or arising from, right? So if you wish, it's a partial trace. I will define it a bit more formally later. Right now, it's actually not so important. We could think of an infinite system, except that it's not very cleanly defined. Later, this will all not matter much. OK. Now, if we define this over mixed states, this will actually be a convex set. That's very nice in principle, because it means, so what do we have to do? We have this convex set S of allowed physically reduced two-body density matrices. And we have this trace over a density matrix times a Hamiltonian, which is a hyperplane, right? The constant energy surfaces are hyperplanes, because it's a linear function. So what we want to do is we want to shift this hyperplane in the direction of decreasing energy. So the arrow indicates decreasing energy until we touch the boundary of this set. And this will exactly give us a ground state energy. Now, that's a convex optimization problem, right? We're trying to minimize a linear function over a convex set. That's great news. Convex problems are efficiently solvable in principle. But, of course, we know that the ground state problem is hard, right? There's complexity results and all these kind of things. So it can't just get easy. So where did the difficulty go? The difficulty went into characterizing the set of these two-body reduced density matrices, right? That's a problem which is just as hard as the original problem, because if we could solve this, right, even decide membership in that set, there are efficient solvers for the semi-definite program. Right? So the problem of deciding membership in S is hard. I mean, we could make complexity theoretic statements, but it's not so important. The point is that this is a hard problem because it basically is a translation of the original ground state problem. So that's just as hard, but it's a different formulation of the ground state problem. And now we can approach this problem in two ways. So what we can do is we can ask, do we have a way of approximately deciding if we're in this convex set? So we can try to find an approximate solution and now there's two ways of doing so, right? One way is basically a variatial. So two ways. One is a variatial approach. So we write down a global wave function psi, or maybe a global density operator omega, which is translation invariant, and take the partial trace. And what will happen, so unfortunately there's no colored chalk, so we'll have to deal with white. What will happen if that's the original set S? Our variatial family will, as we enlarge it, give hopefully better and better approximations of that set. And hopefully what happens is not what I've drawn here, but what happens is that it approximates that set particularly well at the point where the plane will touch. So say if that's our plane here, we want to get this energy. It should touch here, and it should, this is what I drew, but it should also improve most here, right, as we increase our family. So that's one approach. This will give upper bounds to the ground state energy, because I'm trying to minimize. I will find the best state in that family, right? So this will give upper bounds, and that's rigorous upper bounds if I have an actual wave function on the ground state energy or ground state energy density. The second approach, and that's what we're looking at here, is outer approximations. To this set. So what we want is we have this set S, and we want to find a somewhat larger set should have drawn it differently, right? And we want to find less and less, like tighter and tighter outside approximations to the set if we have a sequence of problems, which get, again, closer and closer to the correct set. So if we're trying to do the minimization, we will be somewhat outside of that set, of the proper set, right? Because we're minimizing over that bigger set, or extremalizing over that bigger set, but hopefully, again, quite close. So again, this gives upper bounds. This gives lower bounds. Why should we care? Good question. It depends what you're after, right? I think in principle, whenever we want to make rigorous statements or precise statements about systems, we should have both upper and lower bounds on the quantity we're looking at, right? Otherwise, we don't really have a strong argument for how good our number, say, for the ground state energy is. I mean, of course, people often use variational methods. They're better established. And once you build trust in the method, you probably know how close you get to the ground state. But I would kind of argue the reason why people trust them and build that trust is because there were no good compatible methods. There's other settings where it's important. So this whole question of being outside of convex sets, if you don't think of ground state energies, but other convex sets, any probabilistic theory is a convex set, basically, right? Because probabilities have a convex structure. So if you're asking, I have a local hidden variable model, right? What can that describe? Which is basically saying, when can I be sure that a state is not described by a local classical theory? That's a convex set. And then you want to be sure that you're outside of that set, right? That you have observed true quantum correlations. And for that, you must be sure to be outside of that set. So you must have a larger set which you can characterize and prove you're outside even of that one. Or if your theory is quantum theory, which is convex, right? You want to design an experiment which tells you for sure that you have found something which violates quantum theory. Again, that's the kind of things you need, right? You need outer bounds to the set of all quantum correlations. So in many scenarios, finding these outer approximations is even fundamentally more important. And I'm actually happy to take any input about where this might be interesting as well. Good. Okay, so what I would like to describe is basically a way of systematically forming relaxations to this convex set here, which is much more efficient than naive relaxations of the problem.
That's a very naive question. For the invariance, so insisting on that omega is translation invariant, is there a nice relaxation of that?
Say again?
Is there a nice relaxation of the condition that omega is invariant?
We'll get there. We'll get there. Okay. Actually, quite soon. Okay, I have to think. At some point, there's something I need, and, well, I might screw it up. We'll see. Yeah, exactly. That's the problem, right? You think it's all symmetric. I put any blackboard in front. I can't. Okay, but I think we'll be fine. That's coming on the next page. Well, that'll be fine. Okay. Okay, so what we're looking at is this minimization problem of ρ2 in omega, arising from omega over this linear function. And again, we're looking at translation invariance. The whole argument can be generalized. It's just more writing and, more variables and everything. Now, there are 3 steps we will do. I mean, I'll always write the minimization because that's a problem we're actually looking at. But in the end, it's about characterizing the set here. So it's a 3-step process. And steps 1 and 2 have been around. Step 3 is a really new one. So what is step 1? Step 1 is to expand this statement that ρ2 is consistent with a global state omega, so a reduced state, telescopically. So what we will say is that, well, ρ2 is consistent with another state ρ3, consistent with a state ρ4, and so on. Consistent with a state ρn. And that's consistent with omega, which is a state on some capital N sites, which is much larger, maybe infinity. If you're worried about the infinity, we will drop it soon. So here ρk would be the k-body reduced density matrix. And what we impose is that ρk is larger or equal than 0. and the trace of row 2 is 1. It's sufficient to impose that because they're defined via partial traces, so imposing one trace will be good enough. Now, what does this notation mean that row k minus 1 comes from row k? Let me make this more precise. And it is what you expect, but there's kind of a non-trivial point about it. So what I mean by that is that I get row k minus 1 as a partial trace from row k. But there's two ways of doing that, right? I could trace the leftmost spin, or I could trace the rightmost spin. Right, and that's a condition I impose for all k. And maybe that answers your question, but that's kind of a weak way of imposing translation invariance, to impose this up to the top level, right? If I expand this all the way, I mean, even if you forget this, just imposing this part of the condition. Because actually, if you iterate this condition, it's not entirely obvious, but well, maybe it is. If you iterate this condition, you find that it implies that all the reduced density matrices on any level are automatically the same. So actually, you don't need to impose this condition everywhere. In the end, if you impose it, it will be true for all reduced density matrices. So you could break it at the lower levels, basically. Right, so we will use some graphical notation, and let me introduce it. So we will denote, it's kind of a, if you wish, tensor diagram notation, tensor network notation. Also, tensor networks will only really enter at the very end of the talk. So that would be a three-body reduced density matrices with cat and bra indices. We could omit the cat and bra and just draw one level, but then I would get confused because I'm not used to that. And then we have this partial trace operation tracing the leftmost index, and that should be the same as the trace of the rightmost index. So that's the kind of conditions we would impose.
So,
yes?
Can you just explain again what you mean with trace left and trace right?
Okay, so
I don't understand.
Okay, so we have this density matrix, right? Say on 5 spins. So we have this CD, tensor CD, and so on. Right, and we have some density matrix, some state. What's your background, just to know in which way I should answer?
I just
physics. Sorry. Okay.
Trace of the leftmost,
yes,
or
yes,
of
yes.
the left half of the chain.
No. I have k spins, and I want to get to k minus 1, so
okay.
it's only one spin. Okay. Fine. It's about the.
Or amplifies this way or that way.
Yeah.
You add one on the left or the right.
I think I have to ask her what the background of people is. It's easy to make wrong assumptions. Right. So I mean, this is completely redundant, right? I'm just introducing extra variables which make my life harder because I still have this omega here, right? I just have more variables. At some point, hopefully, our life will get easier. That's the grand plan. Okay. Right, so that's something we then term the LTI condition, standing for local translation invariant. And as I said, in principle, we could just impose it at the top level, and that would be good. It's just inherited through the chain. Okay. Okay, what do I want to keep? Yes, that's good. This one is movable. That's even better. Let's just move this immediately to the middle. Okay. So we could do the same for non-translation invariant ones, and this would widen up tree-like, right? There would be many row 2s, and it would be like a tree of more and more reduced density matrices for different parts of the system with more and more consistency conditions. It would be a mess to draw, but you can see it works. Now, second step. Step 2, we cut this sequence at some finite level. So we dispose everything here. That's why I wrote it like this. So let's call this equation 1. At some finite n. So this this results, I mean, this is a convex problem, but potentially an infinite, if I want this to be extremely big or infinitely big convex problem, doesn't really make sense. If I cut it, it will be a finite problem. And the point is, if I cut it, I just drop constraints, right? So the set of possible solutions will get larger. The radical version would be to stop it here. Then all two-body reduced density matrices, like the singlet state, would be admissible. That's clearly wrong, right? We have monogamy of entanglement. Here it's just saying it's consistent with an n-body state which has this local translation invariance condition. So what do we get? Let me just write it out explicitly because we will need it later, which means the blackboard behind this one is lost for now, but this will be fine. So that's the first step. The next step is that we have some positive rho 3. And rho 3 has a property that if we trace the leftmost spin or if we trace the rightmost spin, we get rho 2. And let me write rho 2 in the middle. And let's hope this is not a mistake. Well, I mean, the equation is correct regardless of in which order I write it, but I want to explain certain things in a certain order. OK, and I will write 2 more, and it's not really to bore you. I apologize. It's really more because I will need them later on. Rightmost, and I need rho 5 because it's surprisingly hard to count accurately to 5 on a blackboard. Okay.
We also impose the also from symmetry.
Sorry?
Also from statistics symmetry.
Well, for now we're looking at spin systems, so no, but you can impose symmetries in that, right? I mean, adding symmetries on everything I'm telling is extremely straightforward. Some other things I'm claiming it can be generalized are also true, but much less straightforward. Yes?
So in quantum information theory, we somehow ask our questions to two states have the same purification. Is that not very closely related?
Say again?
Asking whether they have the same purification.
So which questions? Sorry,
The purification of a density.
Yeah, I understand that, but
Right. So isn't that equivalent sometimes of saying that two states have the same purification, some large enough? At least one of the qualities, right?
No, but because it might not be it's not about pure states, it's about density matrices, which is a much more difficult space, no?
That's true, but I mean, at least the standard tool is to look at purifications of density. And they always have a canonical one, but if you have that property, there has to be this Ullmann map between two of them, right? At least that's one way, I've seen kind of questions handled.
Okay, so I think so. Okay, I'm not sure I see the connection. Okay, potentially, but I really don't see a connection. That's why I'm struggling to provide a succinct answer. If you omit half of the equation, right, and you only look at this half, it's something like a question about purifications, right? But of course, the whole essence is that we want to keep the property, in this case, that we have a global translation invariant state. So it is important that I can get rho 2 from rho 3 in two different ways,
so it's
right?
a question of, in my language, about purification plus symmetry, right? I mean, so that you can swap it to the other side.
If you wish, yes. If you like that language, it's completely fine, yes. It's asking about having a sequence of purifications which are basically translationally symmetric in the specific case. That's indeed a way to view the whole problem. Okay, and then this goes all the way to rho n, right? Which should also be positive and satisfy the same condition. Trace left rho n is rho n minus 1 is trace right rho n. Okay. So the great thing is if we do this, this is a finite semi-definite program. Okay, if I put it here, I will have to, doesn't matter. Okay, so what we get is a finite semi-definite program, right? So a finite convex problem we have to solve. So it can be solved, and this is actually being done to solve these kind of problems. So what we actually see if we do it is that if I look at the log of the error, so if I do a log plot of the error in the ground state energy density versus the level to which I go, I will see an n to the minus 2 scaling in the case of critical systems. And actually a superpolynomial scaling for gapped systems. Now actually the superpolynomial scaling no one could see because you couldn't push n far enough. That's really something we get from our method, which plugs on top of that and provides an upper bound to this curve. I mean, this comes from below, right? This number is negative, if you wish, right? We're below the ground state energy. Now the point is that's actually not such a great scaling, right? Because it's exponentially costly if we have this quadratic scaling in the energy density, right? Because n is, of course, the number of bits, of qubits I keep here, or qubits or spins, right? So I need to store a density matrix of that size. So my memory will really go like d squared to the power n, so it will be exponentially in n. So that's actually not such a great scaling, right? The cost is, it's exponentially costly to get a certain approximation. So this is used, but it's not very practical. So what we would like to have is a better way, or another relaxation we can plug on top of this. And this is what I would like to do in my talk.
So that's something very stupid. So if you do come from an infinite invariant state, isn't it the case that it really doesn't matter where you put the loop up to some sort of cyclic shift?
Well, not once I did the first, right? So at some point I cut.
But any one loop you can do, right? And then you just cyclically shift everything.
But you're asking about here? No, here I can't put it anywhere, right? Because, I mean, what I do is I start from, say, a ring of spins. Then I trace one. Now, right? Now this and this point, these are really ends of, I cut it open, right? I agree. If you, sorry? In the first step, no, of course. I mean, it's translation invariant, right? I'm just saying in this picture, it matters I trace out the left and rightmost because this is after doing the cutting, right? I stopped somewhere and maybe I wanted to be compatible with an infinite translation invariant state. I mean, the thing tells you a few things. It tells you, for instance, whatever bound we get from this thing, it can't be better than n sites which are translation invariant because there I could, or n plus 1, well, actually n. Right, so you can link it to what you can get for either open or periodic boundary conditions with a translation invariant system, because you can't really tell where this comes from, right? And you get the lowest energy, so you have to be below whatever the ground state energy for either periodic or open boundaries on that system size is. Well, open is not true, right? Because for open I have this extra condition of.
Yeah, can you just take a moment to explain the bigger picture? Because I'm sort of missing the connections. So you've got, what's the strategy here?
Okay, the strategy is I have a convex set, right, which is characterized by saying that rho 2 is the partial trace of some translation invariant state on some very large number n of spins, right, which is also a translation invariant state, because I know the optimum can be translation invariant for a translation invariant Hamiltonian.
Yeah, so can you explain that as well?
Which part?
Why does it have to be translation invariant?
Well, what? Okay, so if I have a translation invariant Hamiltonian, right? I mean, if I have any symmetry on the Hamiltonian, right, I can also symmetrize the optimal, any state and get the same energy, right? So thus, whenever I have some energy here, I can as well find a translation invariant state with the same energy. Right? I mean, if H is symmetric, it means H has this symmetry, right? So I can put an integral here, and it will still be h. And then in the trace, I can shift the unitary on omega, and that means I get a symmetrized omega. Okay, more questions?
Yeah, those questions. So when do we have this false negative?
Sorry?
What's the assumption or condition for we have such like log dot E or log US?
Say again? For what?
Like what's the assumption? Oh, sorry. Like what's the condition or assumption we have for?
I mean, that's an empirical. Everything else was completely rigorous, I said. This is a numerical observation. That's probably all I can really tell you rigorously about it. But you know, it's a critical system. I'm sure that if you ask someone who's proficient in CFT, they can tell you why you get the scaling. I don't think we have an explanation, but I'm sure you know. Again, it's critical. Yeah, I'm very sure. I don't think we had an explanation ever, or we're close to one, but we didn't try very hard. But again, I'm sure you can make a CFT model if you want. In the end, you're introducing some cutoff of some kind, and like a length cutoff. So the question is how length and energy cutoffs interplay, basically, in a critical system. So it will relate to density of states questions. More questions?
So I know that you're talking about a one-dimensional system in this case, but if you were to go to a higher dimension, do you expect that the critical exponent's going to change? Is that?
We didn't study it, but it's very hard to study indeed, because you don't get to very large n unless you add a second relaxation level. So what I will explain is that we have a way of kind of finding something which is above this, but follows it very well. It's actually really on top. And at some point saturates, which comes from a second. So here we introduced one cutoff, which is this n. We will introduce a second cutoff. And this will lead to a saturation, but we can push it very far, right? So depending on the model, we can push it to an effective n of between 60 and 120, which is far, I mean, again, two-level system or so. I mean, do the math, it's far above what you can do, right? And this, for instance, allowed us to see that this curve goes like this if you have a gapped system, because our curve goes like that and then saturates. But no one had seen that before, because you couldn't just go to a big enough n, right? So I have no idea what's in 2D. 2D is extremely challenging, even with the compression, because things just go much faster. I mean, we're working on 2D, but it's hard. More questions? Okay. So. Let me maybe put this next to this one, so we have to walk less. Okay, so step 3. I mean, this is something people had done. Step 3, and that's what we did. So what's the starting point? The starting point is if we look at these equations here, right? What happens? The variables in these equations get bigger and bigger and bigger, right? That's quite a mess. Then again, we want these equations are meant to talk about non-trivial mutual constraints between the different variables, right? Like tracing something of something else. But on the other hand, if you look here, no. These 3 sides appear here as well, right? That's the same 3 sides. Or conversely, these 3 sides, which are the same as these 3 sides from the other side of the equation, appear here, right? So the middle sides are actually not touched in any line of the equation. They will be touched somewhere later because we have to arrive at a 2-body density matrix. But looking at a single line, the middle indices are not touched. So observation. Middle indices remain untouched. Actually, when did we start? Did we start at 2:30 or a bit later? We did start in time. I have no idea how long the... Okay, okay. I think we're doing well. Okay, so that's equations 2. Just to follow my numbering, to the extent I... So now, these remain untouched, so maybe there's a way to compress them, right? To throw away some information, because maybe these don't, we don't, I mean, one observation certainly from variational wave functions that you don't need the full Hilbert space usually, right? Or also an insight from renormalization, right? If you look at ground states, we look at a block of spins, we can throw away configurations which have a very high energy locally, because they will not be very relevant in the actual ground state on a big chain, right? We'll only introduce a small error. So maybe we can try something similar here. We can try to throw away certain degrees of freedom in a way where hopefully we don't lose important properties of the system. So the idea is that maybe we can compress. Of course, we have to make sure that in the end we enlarge the set of states we consider, right? We need to further relax things. If you think of the convex sets which are just erased, they have to get bigger in everything we do. Otherwise, we don't know that what we did is what we actually wanted to do. We don't know we really get a rigorous bound. Okay. So let's look at this equation here. And let's try to compress it. So this equation really consists of two equations, right? So one equation is the left trace of rho 4 is rho 3. And the other one is that the right trace of rho 4 is rho 3. And it makes sense to write them separately because the middle picture is a bit misleading, right? If I number these 1, 2, 3, 4, then this is 1, 2, 3. And if I number this 1, 2, 3, 4, this is 2, 3, 4, right? So this is rho 3, but it comes in two different ways from rho 4 if we try to relate variables. Right, so now we would like to compress rho 4. So we would like to take these two indices here and compress them somehow. So how would we like to do that? Well, so we would like to take rho 4 and replace it by a new variable where we take rho 4. And okay, how to draw this? Here I have it in green, so it doesn't really matter. Let's draw it like that. So let me call this V4. And that's V4 dagger, right? So in that case, I'm just applying, say, an isometry for convenience, but it could actually be any linear map. It should go to a smaller space. And now you might rightfully object that if I do it for two sides, likely there will be no good smaller space. That's true. If you actually do it, you might have to go to 8 sides, and only then you can start compressing, depending, how much information you want to keep. Same as for renormalization. If you want a good renormalization scheme, you will probably not renormalize 2 sides, but more sides. But for the purpose of illustrating it, that's nicer. And this I will call sigma 4. And there's this thick compressed middle leg here. And now I can reinsert this into this equation here, right? So what I get, write this here. So I take this equation up here. So let's take the first one. Let me call this 3a. So if we take 3a and we apply, so we take it, which is that rho 3 and rho 4 are related by this trace on the left. And now I apply this map V4 to this equation on both sides. And here I have to apply to the left 2 legs. This equation implies this equation, right? Which means it's a weaker constraint. If I only impose this equation, there might not be a rho 4 and a rho 3 which actually satisfies it, right? Therefore, it is a relaxation. I enlarged my search space. That's good. That's exactly what I wanted. And well, this is exactly what I called sigma 4. But now I've traced the leftmost index. And I can do the same on the right, and let me just do it, because again, we will need to combine them at some point. So we have sigma 4 with a trace on the rightmost index is equal to the compressed rho 4, again with the same V4. Here. That's rho 3, where now I have compressed the right indices. So that's equation 4, 4a and 4b. Okay, so by introducing this V4, I did compress something, namely now I will kick out these variables, right? Here. That would be the idea. I only need to store sigma 4. I don't have to store rho 4, which is a smaller object. Now, sounds great. However, the problem is that rho 4 still appears in this equation. Let me erase these arcs again. Right, rho 4 still appears in this equation. And of course, it's completely useless to compress rho 4 in one of the equations and replace it by something else if I have no way of replacing it here. Now, however, of course, here what I would like to do is actually to compress rho 5, which will require compression acting on 3 sides in the middle, right? So the point is I need to compress rho 5, and at the same time, I need to find a way to consistently compress rho 4 with both compressions, right? So I can replace it by the sigma 4. So that's what we need to do. So let's look at the compressed rho 5. So what we have is that we take rho 5. Oops, counting to 5. Wow, it's really bad. Let's put it on the jet lag. Okay, so there is a V5, right, which is now compressing the middle 3 legs and giving us sigma 5. And again, the philosophy would be that the compressed system should have a constant size independent of the level k. It's not mandatory. You could choose them differently, right? It might be smarter to let them slowly grow, but the philosophy is same size. Thus, each of these objects has the same memory requirement, right, independent of the level. Okay, so now what we have is we have sigma 5. Oops, sigma 5 is the compressed thing with a left trace. So I'm just basically copying these 2 equations again. So we see what we have to put together. That's a compressed rho 5 with this compression V5. And that's, sorry, I want to put rho 4 here. Right, so I'm really just taking the rho 5, rho 4 equation here and applying that compression. And again, this is V5 here. Okay, the same we have from the other side. V5. Like this. Now, what do we want to do? We want to get rid of rho 4 in this level altogether, right? I mean, one important thing to note about this sequence of equations, say rho 4 only appears in this equation, right? So each of these rho k's will only appear in 2 consecutive equations. So if you understand how to eliminate one of them in 2 consecutive equations, we can put these things together and eliminate all these, or well, compress all these variables. So what do we need to do? Well, so on the one hand, we have this thing here, and this thing here, that's the objects we need here, right? We need rho 4 compressed with a compression for rho 5 in 2 different ways, on the 3 indices on the left and the 3 indices on the right. On the other hand, we have sigma 4, right? So we want to re-express rho 4 in terms of this object here, because this is the compressed object, right? So how should we do that? Oops. Okay, which board is the best? This one. Should I leave it here or should I move it to the right? We will mostly stare at these things there. Just wondering if it's better. Let me move it here. If you feel you want to look at this equation, tell me. I just felt it's nicer to have things which I want to talk about close by. So what we want to do is we want to be able to take this thing and express it as a function of this thing here, right? Because this is our compressed variable. So one way of doing it, and that's a sufficient way, is to have the following. So we want to be able to compress the row 4 where the 3 indices on the left have been compressed. V5 as a function of row 5. Oops, what? No. There is no row 5, right? I forget about everything else. I only want to talk about row 4 and sigma 4. My apologies. Okay, so I want to re-express this in terms of sigma 4 of this thing here, right? Which is, so let me remove this equality sign. So I want to re-express it as V4, which is nothing but my compressed variable sigma 4, with something up. I want to get these sides equal. So what's my best hope? Well, I'm not sure the best. Let me draw this in a more square shape. Well, the idea would be that I have some additional compression L5. Did I call it L5 here? Yes. Right, which I apply here. Again, the thing down here always has a dagger. I just don't write it. Such that this is equal, right? That would be the first thing. And I want the same for the converse statement, right? I also want that row 4 with that thing applied to the right. Oops, no, 4. Yes. Oof. Should again be equal to the thing where I compress the middle indices, because that's sigma 4. Okay, I realize, of course, here, if I put this, I have to put the L also on this side of the equation. Compressed. And same philosophy here, just I compress on the other side, right? So I do an R5. So that's a sufficient way of doing that, right? It's maybe not the only one, but if I manage to find that, it will certainly do. So how do I achieve this? Well, the easiest way is clearly to achieve that this thing is just equal to that thing on the top, right? So what we want is that, oops, if we take V5, it can be decomposed either this way or that way, right? So it can be decomposed as putting this L5, oops, which way does it have to go? This way, times V4, and conversely. It's full. These are 2s squares. So that's the kind of equations we want to solve. If we find a way to solve these equations, we have found a way to compress the system. Let me not rewrite all the equations from the original problem in this compressed language. If there's time, I will do so at the end. But the point is that if you, oops, that was one too many. Right? If we have these ways of rewriting things, we can just substitute our rho 4 in these equations, actually right here, right, by something which depends on sigma 4. So in the end, we only have sigma 4 conditions here. Good. So how do we solve these equations? So what we want is we have these equations for all k, right? So we want a more general equation, which tells us that if we have a vk, there's an rk plus 1 and an lk plus 1 such that we get the next compression. So we want it at all levels, and now you might object, well, these objects are still extremely big, right? I can't store these compressions. These compressions are also exponentially big. However, if we do it consistently, and I will write it for the actual ansatz we get using tensor networks, you will see that all you ever get in these equations are Rk and Lk. The V's all drop out except in the very first level, right? Because the V's are used in the definition of the sigmas, and if we do this consistently, we only use sigmas, and the sigmas have been exactly defined in a way where we have already applied the compression, right? As you can see, the sigma to the sigma, I only need to apply L to get this kind of equation, which I need. Okay, so how do we do this? Well, there's different ways of doing that. And the idea is that whenever you have a renormalization scheme, there should be a way to come up with a scheme. 10 minutes? 5 to 10, yeah, I think that should be fine to give the essence. So whenever you have a renormalization scheme, I mean, this looks a bit like a normalization one way or the other. You don't have to do it exactly like that. You could compress with different ways. You could use completely positive maps, compressing the cat and the bra at the same time. So there's a variety of ways of doing that compression. Okay, so what we propose for one dimension is a 1D tensor network, which is translation invariant. So the idea is that what we would use is, in case, let me just briefly write it, because maybe not everyone is familiar with tensor networks. The idea is that we have a bunch of, so each of these things denotes a 3-index tensor. And so this is an A which depends on alpha, S1, and I1. It's a 3-index tensor, and they're all the same 3-index tensors. This has A, I2, S1, S2, and so on. There's an Sk minus 1, Ik, and some beta. So this tensor here is Aik, Sk minus 1, beta. So what this depicts is that I'm multiplying these numbers, these tensor entries, and I'm doing a sum over all the connected indices S1 to Sk minus 1. Now, in which way does it satisfy these equations? Okay, magic question. What should I erase? Oh, okay, this is fine. Experience shows that whatever you erase, you regret it the next moment. Well, this should be fine. So how does this work as such a compression? Well, what we will do is basically to say that our Vk, the object we never actually want to work with, which is this thing which would take k indices, I1, I2 to Ik, and compresses them, is exactly supposed to be such a tensor network. And the idea is that this compressed index here is really a double index holding this alpha and beta. It's kind of intuitive. You want to compress the bulk and keep the two boundaries, right? So that the compressed thing has mostly the boundary degrees of freedom is something you would expect. Okay, how does it satisfy these equations, and what are the R and the L? Well, if I want to take Vk plus 1, I can naturally rewrite this as this, I1, I2 to ik plus 1. And now the idea would be that this here is exactly my lk plus 1, I guess, right? So that's exactly, did I call this L? Yes. That's exactly the, I just wrote it the other way around. That's exactly what takes the isometry on k sides and adds another side, right? So it's really just graphically twisting the tensor network, and obviously the same the other way around, right? Oops. So that's all one needs to do. And all I need to work with are really these two things. So since I'm basically out of time, let me just write how the compressed semi-definite program looks like, because it's actually quite appealing. So I want to take these equations and write them in a compressed form using what I'm just erasing. That's how efficient the compression is. OK. So what do I have? Well, the first line will stay. I have row 3. Is row 2. And then starting from the next level, what I will do is I will write a sigma 4 here, which now the compressed indices are 2 indices, right? These are my elaborate color scheme doesn't work. Anyway, these middle ones are the 2 matrix product state indices, right, which are pointing up here, this one and that one. And 2 other schemes, legs. And this is obtained from row 3 by applying the matrix product state, or the inverse of the matrix product state if we wish to compress. And there's a symmetric twin, right, where I take, wait, there's a partial trace missing, obviously, right? That should be the partial trace. And there's a twin where I trace the right side and compress the right legs. That's precisely this equation, right? Just that now I put my compressed variable here. Right, you see only sigma is appearing, and starting from the next one, I only ever have to put compressed variables. So what I have is that I have sigma 5. And again, I have to take sigma 5 and compress my left leg. This is obtained by taking sigma 4. And applying my matrix product state to compress on the left. Namely, what I do is I take this compressed leg, I fuse using this tensor A, this leg, and like this, and the same on the other side, all right? So on the other side, I would take sigma 5. Partial trace is OK. And that's it. And you see all objects are of a fixed size of physical dimension, and that's the auxiliary or bond dimension, capital D of the matrix product state to which you want to compress. And well, what can one say? Well, one thing, the memory requirement will scale linearly with the level to which you go. The big question is, which matrix product state should you use? Now, it turns out that the variationally optimized matrix product state for the upper bound, right, it's a good variational ansatz for 1D chains, works remarkably well to compress also for the lower bound. It's not entirely unintuitive, right, because again, what we want to keep are the subspace which is most relevant for the ground state physics somehow, and that's what the upper bound keeps. We tried to prove theorems, but we found counterexamples. They're somewhat contrived. They don't say that it doesn't work, but it seems difficult to prove that it works. And actually, it's not so important to have a super good matrix product state upper bound. It's just somehow good, which is OK, right? It has to capture the correct subspace. You don't care what you do in the subspace. The compression really cares about which subspace you keep. If you distort it, that doesn't change the semi-definite program. The other thing is what I said about the plot I erased, right? There was this log energy versus n scaling, and this went like n to the minus 2. And what you say is you get such curves which saturate depending on the d you choose, right? There's a maximal n. So there's an effective n, basically, which would be this intersection. And the effective n we can reach, I mean, we can go to super big N, right? This plot is just saying you fix how much you compress. It doesn't help you to go super deep in this hierarchy. At some point you saturate, right? Because you don't capture anything new anymore. But the effective N, which is kind of a figure of merit by how much we gained by this compression, we can go to, as I said, Heisenberg 60, simpler model like Ising model 120 or so, effective N, where this saturates. So that's the energy accuracy we get is equivalent to doing the uncompressed thing for up to 120 sites or so, which is, of course, completely intractable. And I guess that's a good point to stop. There's several ideas for generalizations which we're exploring, but I'm happy to take additional ideas for where this might be useful, because these convex problems are, for many body systems, are actually everywhere in quantum information and physics. OK, thanks a lot.